clipping of lines to a clip region. So we looked at the Sutherland-Hodgman algorithm, quite simple. You calculate the distance from a point to the plane, and the sign of that distance determines whether you need to clip or not. That's all very well. That does just a single line clipping. Okay, obviously, if we look at virtual worlds, they're constructed using polygons. So we need a method, a systematic method for clipping polygons, and this is exactly what Sutherland-Hodgman is. It's actually not a lot to it, really. It's just a way of keeping track of what you need to clip and what you don't. Okay, so there's not a lot I can say about this. It might take me about 10 or so minutes to actually talk through this. And what it does is used to determine the vertices of a polygon that is clipped to a clip region. Now, the example I'm going to use, the clip regions normally have about 4 sides. In practice, you have your screen space is bounded by 6 sides because it's a cube. But we're just going to be looking at simple 2-dimensional examples. What we do is we start with a polygon that is defined by a set of vertices. So if you got a program, for example, the ones you did for your assignments last term, you had a poly list. And the poly list is simply what vertices define the polygon, the corners of the polygon. Okay, so each V1, V2, etc. is some coordinates. Okay, that's just a vertex for that polygon. And what we do is each edge of our clip region is checked to see if the vertices are in front, on, or behind. We do that using the method we looked at this morning. Okay, so we have to do this for every edge of our clip region. So if you've got a unit cube, you've got 6 edges. Any polygon edge that intersects with the edge of the clip region, we clip using Cyrus-Beck. So calculate the distance, calculate t, then you calculate the clipped point. Here comes the important bit. Vertices that are behind the edges of the clip region are removed from that polygon list. Okay, so here, if we start with this list, let's say V2 was behind our edge, then we simply remove V2 from poly and we replace it with clipped vertices. Okay, the Sutherland-Hodgman algorithm is something which I'm going to show it to you in a minute in the formal sense. It's a lot easier actually doing it in practice than it is to show you in the formal sense. And I'll go through a work example with you. Okay, so this is the formal way in which we presented the Sutherland-Hodgman method. Okay, what do? We start with an n-sided polygon with a vertex list poly, which just contains the vertices in that polygon. And we also have an m-sided clip region with some edges. Okay, typically, usually in practice, you've got 6 of them. There's 6 sides of a cube. Some of the examples we'll be going through in a minute, they just got 4 sides. Okay. So what we do, we start off by setting a variable k equals 1. This is the number of newly created vertices. Okay, so every time we create a new vertex, we're going to add something to k. Okay, we've got a couple of nested loops. So the outer loop loops through the edges of our clip region. So if you had a cube, that will be for i equals 1 to 6. The next loop, the inner loop, loops through the edges of our polygon. So we start with one edge of the clip region, and for each edge of your polygon, you test it against that one edge. Once you've finished that, then you move to the next edge of the clip region, and you test each edge of the polygon. Okay, so this is a couple of loops. So loop through the edges of the clip region, loop through the polygon vertices. And here we have a test. Okay, what we do is we test the current vertex. So J is a vertex number. So if j is 1, we test the first vertex and the second. Okay. If they're both in front, and how we do that is we calculate their distance between the point and the plane. If they're both in front, what we do is we add the vertex j to the vertex list. So at the start, new poly, I'm going to create a new vertex list. This is empty. Right at the beginning, this is empty. And what we do is we add to it. Okay, so we have our poly list, which is what we start with. What we're going to do is we're going to create a new list, and we keep adding to that list. And so in the end, we replace poly with new poly. Okay, so if vj is in front and vj plus 1 is also in front, we add vj to the vertex list. If vj is behind and vj plus 1 is in front, then we clip vj to the edge and calculate the intersection point. I've called the intersection point ik. So remember, k is a number of newly created vertices. Okay, so if k is 1, and let's say that's our first intersection point, then I've calculated I1. Then we add I1 to vertex list. So instead of adding vj, we don't add it because it's behind our edge. We add the clipped point. And because we calculated a new vertex, we increment k. If it's the other way around, if vj is in front, but vj plus 1 is behind, what we do is we clip vj plus 1 to create I, the intersection point, and we add vj and the intersection point to our new poly list. Okay, so that's the Sutherland-Hodgman algorithm. After you've done that for one edge, you replace poly by new poly and do it all again. So that's done for one edge, and then you do the same for the next edge, same for the next edge until you've done all edges. At the end, your poly should be the vertex list of your clipped polygon. Now that's quite difficult really to understand just by looking at this algorithm. Presented in this way is not intuitive. Okay, it's presented in this way so it makes it easy for when we need to program it. Okay, so what I'm going to go now is have a look at a worked example. Okay, so this is also on your notes. So here we have a star-shaped polygon. Okay, so this sort of blue polygon here, that's the polygon I want to clip, and this rectangular edge, rectangular clip region is what I want to clip it to. I've labeled the edges E1, E2, E3, E4 just for convenience. And the vertices are labeled V1, V2, all the way around to V10. Okay. So my initial vertex list are just my 10 vertices, V1 to V10. Okay, so what I'm going to do is I'm going to go through the steps of the Sutherland-Hodgman algorithm. First thing we do is we check E1. So we check the first edge. Okay. So starting at V1, I check V1 and V2. V1 is behind because this edge, remember, all the normal vectors face in the interior of the clip region. So the normal vector for this plane points straight up. V1 is behind the plane, V2 is in front. So what I do is I clip V1 to this point here, which is I1. And I do that using Cyrus Beck. We looked at that this morning. And add to new poly. Okay, so what I add to new poly is I1. Okay, V2 all the way around to V7, they're all in front. Okay, I've checked each of those in turn. I'm not going to write them down, obviously, but you can see by visual inspection, this point, all of these points are all in front of this plane. Now, when it comes to V8 and V9, V8 is in front, V9 is behind. So I clip V9 to I2. So I've clipped this point V9 to this point, and I've called it I2. And I add V8 and I2 to my new poly array. Okay, so far I've added I1, V2 to V7, V8 and I2. Okay, check V9 and V10. V9 is behind, V10 is in front. So I clip V9 to I3 and add I3 to new poly. Okay, V10 is in front, and V1, so I've gone all the way round, back round to V1, is behind. So I clip V1 to I4 and add V10 and I4. So one thing you should notice about this, it's done in a very systematic manner. It's quite simple, but it has to be done in a systematic manner. So, okay, if I look at my my list now, my poly array, what I've done is starting at V1, that's not included, but I1 is, because it's the clip point. V2 to V7 is included. V8 is included, but V9 is clipped to I2, and it's also clipped to I3. V10 is included, and finally V1 is clipped to I4. So that is now my polygon, well, that defines my polygon which has been clipped to this bottom edge. So that's the first edge done. Okay, so that's what my star shape looks like now. So after I've clipped to the bottom edge, you can see the bottom two sort of spikes have been sort of cut off. Okay, what about the second edge? Well, this normal vector points to the left. Okay, this is my edge 2. And what I do is I start at I1 and I check each of these in turn. So I'm looping through this loop now. So I1 is in front, add to new poly, easy. V2 is in front, but V3 is behind. So what I do is I clip V3 to I5, and I add V2 and I5 to new poly. V3 is behind, V4 is in front. So again, I've got to clip V3 to I6 this time, and I add I6 to new poly. Going all the way around, V4 to I4 are all in front, so just add them. Okay, so now my polygon looks like this. So essentially, instead of V3, where are we? Instead of V3, I've replaced them with I5 and I6. Okay, do the same for the third edge. Okay, that's the top edge, so the normal vector is pointing down. As you can see from this one, everything's okay apart from V5. Okay, so V5 is behind, so I'm going to have to clip to a point there and a point there. Okay, so add all the ones. Oh, sorry, V4 is in front, V5 is behind, so we clip V5 to I7, and we also clip it to I8. Okay, so instead of V5, I've got I7 and I8. And finally, we do the last edge. Okay, so I1 to I8 are all in front. They're fine. 7 is behind. V6 is in front, so we clip 7 to I9. And we're also going to clip it to I10. V8 is in front, that's fine. I2 is behind. Now remember, I2 was a previous clipped point. Okay, just because it's been clipped in the past doesn't mean it can't be clipped again. So I2 is clipped to I11, and it's also going to be clipped to I12. Okay. And our final polygon array or polygon list is that at the bottom. So it's a mixture of original vertex coordinates, so V2, 4, 6, 8, and 10 have all remained unclipped, and the odd vertex coordinates have all been clipped to I values. So what you then do is you then pass your whatever the polygon is over to your plotter, and that plots the clipped polygon. Okay, so it's a very systematic method. It's quite a simple method. It's simple to actually do by visual inspection. It's not quite as simple to do by programming. Okay, so that's a Sutherland-Hodgman algorithm. Okay, what I'm going to do is just go over to MATLAB briefly. How do you get the downloads from here? Never mind, I just... Okay, so if I just use some... here we go. Okay, so this is your unclipped screen space. Okay, so as I mentioned previous in the week and this morning, okay, when we apply projection and scaling, what we do is we get the viewing frustum, okay, is then a unit cube. So if I sort of zoom this around, so looking from on top, you can see the close. So we're looking at this point going up. Okay, this house here was closest, so it looks bigger. You can see it sort of skews it a bit. It skews it and just using perspective. So if I sort of zoom, rotate around, okay, you can see what's happened. So you can see here, we've got this house actually, it's half inside, half outside of the unit cube. So we're gonna have to clip this house to this edge and this little corner here. Likewise, the back of the church needs to be clipped, and so does this end. Okay, that's the unclipped screen space. Okay, so that's what happens when you apply that projection matrix. Okay, the other one. Okay, this is what happens. Okay, so if you do, this is the sort of the hardest task from assignment 7. This is what happens after we've used Sutherland-Hodgman. Okay, if I look at it from on top, you can see that house there is being clipped, and so is that edge, and so is the back. So if I sort of zoom around, you can see they've sort of been cut off, and on the back there as well. Okay, so if we look at it from the angle which we should be shown on screen, if I can just get it, not playing nicely. Oh well, let's come something like that. So that's what the image of the virtual world should look like when we start dealing with plotting it on screen. Okay, what I'm going to do now is just hand out some of these activities. Like this morning, I need to go through. This is one I wish you would talk about. Okay guys, so this is another one of the activities, just to sort of go through another example. I'm not going to take too long on this because it's quite self-explanatory and quite simple. Okay, so this is taken from a previous exam paper, part of the question. And here we have some polygon defined by vertices V0, V1, V2, V3, and V4. And we have a clip region defined by edges E0, E1, E2, and E3. Okay, so essentially what we do is we test, we go through each edge. So first I'm going to look at each edge. And if I go around the, so my polygon list to start with is equal to V0, V1, V2, V3, and V4. Don't know why I started at V0, doesn't really matter. Okay, so if we look at edge E0, V0, V1, V2, V3 are all fine. We don't have to do anything with those. that V3 to V4 needs clipping. So you can see V3 to V4. So I have, that's my plane, there's my normal vector. That needs clipping. Okay, so what I do is I clip V4, and I'm going to create a new intersection point there. So that's my first one, so I call it I1. And I'm also going to create this one here. So clip V4 to I1. And also we have V4 to V0 needs clipping. So I'm going to clip V4 to I2 as well. I2 is going to be that point there. Okay, so the current vertex list. So my polygon list is going to be V0 was fine. So was V1 and V2 and V3. But instead of V4, I'm going to have I1 and I2. Okay, so that's that edge tested. So you test each edge, go around the polygon, testing each edge of the polygon, and clip if you need to. So edge 1, which is at the bottom, it's going to have a normal vector facing up. So if we go through this order, we can see that V0 to V1 needs clipping, and so does V4 to V0. Oh, sorry, I4, sorry, I2 to V0. Okay, because V4 doesn't no longer exist, it's actually I2. Okay, so V0 to V1 needs clipping. So we clip V0 to I3. So I'm going to call that point there I3. And the same applies from I2 to V0. So I'm going to clip V0 to I4 as well. And therefore the poly list is going to be I3, V1, V2, V3, I1, I2, and I3. Okay, and we do the same with the other sides. So V2 is going to be clipped to I4 and I5. Okay, so just going to have to use another piece of paper. Just going to overlay with another piece of paper here. So if we clip to edge 2, we've got V1 to V2 needs clipping and V2 to V3. So we clip V2 to I4, clip V2 to I5. So the poly array or the poly list is I3, V1, I4, I5, I1, oh sorry, V3, I1, I2, oh, that should have been I4, shouldn't it there? Sorry about that. 5, 6. That should be 5, 6, 1, 2, I4. Okay, so hopefully you get the idea. How do we know if they need clipping? Well, we use Cyrus-Beck. We look at the distance between the point and the plane. And I suppose for completeness, I should do the last one. Oh, that that was E2, was it? Sorry about that. E3. Okay, in this case, okay, V3 to I1 needs clipping to that point, which will be I7, and I1 to I2. Because remember, we're looking at this line here, this plane. It's got a normal vector pointing down, and that gets clipped. Call it I8. Okay, so the last one. Okay, so the completed vertex list going around. That. You can see by visual inspection, it's quite an easy method. It's not hard. You just got to take it in a systematic manner. When you code it, it's actually quite tricky. Lots of loops, lots of data to be having to contend with. So for that reason, what I've done for the assignment is I've given you some skeleton code. I'm going to talk a bit about the assignment now, actually. So I'll let you jot that down, and then let's have a look at the assignment. Okay, I'm just going to bring up the Moodle area. Okay, so for the 7th assignment, let's bring up what the assignment is. Okay, the first question in the 7th assignment is essentially a hand calculation. I think some of you have already done this one. Okay, so question 1 on assignment 7. First question 1A is to calculate that projection matrix, which combines perspective projection and the scaling of the VM frustum. 1B, calculate your screen space coordinates. Okay, so multiply your vertex coordinates by that matrix and then divide by the 4th row. Okay, so remember that homogeneous coordinates, we divide by that 4th element. So this gives you some screen space coordinates. Then what I want you to do is use the Sutherland-Hodgman algorithm to clip the screen space coordinates to the edges of the screen. Now, the edges of the screen will be 6 sides of the unit cube. You've got to take them in order. Any order, it doesn't matter, but as long as you do each of the 6 sides. Calculate DA and DB for them all, and then determine which needs clipping and which don't. It's actually quite easy to determine which needs clipping and which don't, because the coordinates will be either less than -1 or greater than 1. So if any coordinates is less than -1 or greater than 1, you know you need to clip that coordinate. Okay, so that's question 1. It might be worthwhile, before you do 1C, to have a go at question 2. The reason being is if you can do it using MATLAB, you can then test your hand calculation, vice versa. Okay, question 2 is essentially write a program that does all of these in MATLAB. I've given you an incomplete MATLAB function which does the Sutherland-Hodgman algorithm, and I'll show you what that is now. Okay, so if we have a look, sorry about this, I haven't given it to you yet. My apologies. Hey, where's it gone? I see something very different on my. Okay, I haven't put it up there yet. Well, according to when I'm on my computer, is up there, but I'll just show you what I mean by that. Right, okay. I'm going to go to... Okay, what I mean by the incomplete Sutherland-Hodgman, okay, I've written most of it, most of the sort of awkward stuff. I need you to input to finish it off. Okay, so this is the Sutherland-Hodgman code, which will be available on Moodle. What it does is the inputs are the vertex coordinates. So those are the individual coordinates of your vertices. That's after you've applied projection and scaling, and you also divide by the fourth element. Poly is your polygon list. Okay, that's, if you've only got one polygon, that's quite simple. It'll only be one line. Okay, this function here only does one polygon at a time. If you've got several polygons, you have to loop through each polygon, apply this function one after the other. Okay, so vert is the vertex coordinates, poly is the linked list, n vert is simply the number of vertices in the polygon. So if you've got a square polygon, there's 4. If you've got a triangular polygon, n verts is 3. Okay, what this function does is it applies clipping, and what it returns the vertex array, including any new vertices that have been calculated. Okay, so remember, as we saw here, okay, we calculate new vertices. So that verts array coming out of it contains any new vertices. Poly array is the poly list for the clipped polygon. N verts is now the number of vertices in that clipped polygon. There may be more vertices, there may be less. After clipping, you've changed the polygon. Okay, so let's have a look at this function. Okay. Anything you need to change in this function is given by 4 question marks. So where you see 4 question marks, you have to write something. Okay, and I'll explain what happens here. This cube verts and cube normal, they're the vertices that define the planes for the edges of the cube. So you can see here the first 3 vertices are -1, -1, -1, all of them. So that's the sort of bottom corner, and the other 3 are the top corner. Okay, so 6 vertices because we have 6 edges of a cube. And we have 6 normal vectors corresponding to those 6 sides of the cube as well. You don't have to worry about that, that's done. Okay, so we loop through the sides of the unit cube. Okay, extract P and N. P is a point on the plane, N is a normal vector to the plane. Loop through the polygon vertices. Okay, verts A is just the vertices of the point A. Verts B is the vertices of the point B. Okay. Then you need to calculate dA and dB from Cyrus Beck. I'm not going to do that. You have to fill that in. Okay, so calculate the distance of point A from that plane and do the same for B. Then calculate the intersection between the line that joins A to B and the current side of the unit cube. Again, that was done in this morning's lecture. Okay, if both A and B are in front, add polygon A to poly. Now, new poly starts off being empty. Okay, you can see it's there. I've created an empty array. To add a number to the end of an array, you simply do this. Okay, new poly is the array, and I've added the number poly A to that array. Okay, so that's if they're both in front. If A is behind, but B is in front, so what we do is we add the clipped point to new poly. Okay, we only add the clipped point. Clipped point will be calculated here. Okay, so new poly, we have to add the clipped point to it. Look at that, that gives you a hint how to do that. Okay, I've given you a hint there how to add the clipped point to new poly. You also have to add the vertices of the clipped point to the end of the vertices array, verts. Again, there's a clue of how to do that there. Okay. If A is in front, but B was behind, we add A and the clipped point. So in this case, we only add the clipped point. Down here, we add A and the clipped point. Okay, so it's slightly different. Again, 4 question marks means you have to write it in. Okay, and that's that done. So this this code will be available on Moodle. If you use this correctly, if you change those 4 question marks and you apply this code here to your verts and poly and nverts, that should calculate all of the clipped coordinates for you. Okay, so that is there to help you for question 2. Okay. The additional task, or 3, is define a unit cube, apply some rotation and translations to it, and then clip it. Okay, with the additional task, okay, I will provide you with this skeleton code. Okay, skeleton code for cube clipping. Okay, again, where you see the 4 question marks, that's what you're going to have to change. Okay, define the vertices of the cube, define your polygon linked list. Massive hint for you. It may be you want to have a look at this section. Okay, big hint for you there. Okay, transform the cube. You've done this quite a few times now. Translate, rotate, apply that. I'm not going to tell you how to do that. Project aligned world space onto screen space. You're given a field of view angle, you're given aspect ratio, calculate the perspective projection, apply it, apply the scaling as well. Okay, that's essentially parts 1A and B. Okay, so that's what you're going to have to do there. What this loop then does, okay, this loops through your polygons. Your cube has 6 sides, so it's going to loop through all your 6 polygons. This applies the Sutherland-Hodgman to the current polygon. So notice poly I and nverts I. And this built bit says, okay, if we have clipped, if the polygon's been clipped or it lies totally inside the viewing frustum, add it to the polygon lists. Okay, so you don't have to worry about this. If the Sutherland-Hodgman algorithm has been done correctly, you don't have to worry about that. And then this will plot the clipped cube and it will plot the unit cube. If I try and run this now, it will come back with an error because I've got all those question marks in it. So it won't run straight away. You have to change it. Okay. And the other thing I want to show you, if I just go back to my Dropbox, I've also got a skeleton code for the village clipping. If you want, you can use your code from assignment 6 or any of your previous code. If you notice in the actual assignment specification, oops, sorry about this, amend your MATLAB program of the virtual world. So if you want to use the virtual world you previously created, by all means do that. Okay, and then you could apply the Sutherland-Hodgman if you want. If you don't feel like you want to do that, where are we? Okay, I've got a skeleton code here. You don't have to mess about with anything. The only thing you have to mess about with is parts 4 and 5. Okay, so this part 4, project align world space onto screen space. So you're going to have to do something here. Okay, so that means creating that matrix, project it. And then part 5, this is where you have to clip it. Okay, at the moment, it's all commented out. So what you'll need to do is once your Sutherland-Hodgman algorithm has been done, uncomment all that. And what you should end up with is, I'm not going to show you, I'm not going to scroll down to show you the answer. But what you should end up is something like this. Okay, so Those skeleton codes will be up on Moodle shortly. Should have been up there now. I don't know why they're not. Okay, that's quite a lot to take in. Are there any questions at this stage? Sorry? The deadline for this one is next Friday. Okay, bearing in mind it's the first week back and it's only been up until now, but you can do it. I don't mind as if you hand it in up to a week late. So bear in mind that. Yeah, any other questions? Are you sort of confident you know what you need to do? So 1 is just a hand calculation. Question 2 is creating a MATLAB program to perform the calculations in the hand calculation. Use the Sutherland-Hodgman skeleton code. Okay. Yeah, so use this code and try and calculate your answers to question 1 using this code. Okay, the answers to these were given in the lecture this morning. Okay. Excellent. Okay, have fun with that, and I'll see some of you later on and some of you next week.